August 17, 1960. 85,000 feet above Sverdlovsk, Soviet Union. The air outside the cockpit canopy was so thin it was effectively black, even in the midday sun. Below, the world was a mottled canvas of green forest and gray city, an impossible distance away. Captain Francis Gary Powers, strapped into the seat of his sleek, silver U-2 Dragon Lady high-altitude reconnaissance jet, was a solitary speck, an invisible eye moving at the very edge of space. His mission was simple: gather photographic intelligence on Soviet missile installations, a task that had, for years, been almost a peaceful monotony. The Soviets couldn't touch him up here. That was the long-standing gospel truth doctrine of the early Cold War. Suddenly, a blinding flash. It wasn't the sun, but something tearing into the perfect void around his aircraft. A thunderclap delayed by the vacuum slammed into the U-2's fragile airframe, followed immediately by the sickening, rapid-fire thump-thump-thump of shrapnel ripping through the wings and fuselage. Powers was instantly battling a dying machine. The U-2 pitched violently, its wings shearing off as it began its catastrophic tumble from the stratosphere. Down below, the successful launch of a Soviet S-2 guideline surface-to-air missile, once dismissed as an ineffective weapon at such altitudes, had just fundamentally changed the rules of the game. The shot heard around the world. The downing of the U-2 sent shockwaves not just through the White House, but through the engineering offices of Lockheed's Advanced Development Programs, the secretive division in Burbank, California, better known by its nickname, the Skunk Works. For months, the U-2 had been the West's only window into the Soviet heartland, a weapon of information. Now, that window had been shattered. The immediate conclusion by intelligence and military strategists was terrifyingly clear. The gap between Soviet defensive technology and Western surveillance capabilities had vanished. The skies over enemy territory were no longer safe. In a small, windowless office, hunched over a drawing board perpetually littered with cigarette ash and discarded calculations, sat the man who had designed the U-2 and almost every other revolutionary aircraft of the past 2 decades, Clarence Kelly Johnson. A legendary figure known for his almost supernatural ability to merge aerodynamic theory with hard, practical engineering, Kelly was a man who worked by his own famous rule: simple, fast, and keep it secret. He watched the news reports, the political fallout, and the public humiliation of the U-2 incident with a grim, fixed expression. His creation had failed. His next creation would have to be immune to failure. It would have to fly higher and faster than any weapon the Soviets could ever dream of fielding. It would have to be an aircraft that, by all conventional metrics, was simply impossible. The challenge was now personal, and the solution demanded a complete, radical break from everything known about flight. The specification handed down by the CIA's most demanding intelligence officers was audacious. A reconnaissance platform that could not only survive Soviet defenses, but render them completely irrelevant. It needed to sustain speeds over Mach 3.0, 3 times the speed of sound, and operate at an altitude consistently above 80,000 feet. At that speed and altitude, the air friction would heat the airframe to temperatures that would melt conventional aluminum and strip paint off the wings. Fuel would boil, and rubber seals would simply vaporize. Every textbook on flight had a warning label slapped across this territory. Kelly Johnson looked at the warning and saw only a blueprint. He knew the problem wasn't a matter of incrementally improving the U-2. It was a matter of reinventing the airplane from the ground up, starting with a material no one in aviation had dared to use as a primary structure: titanium. This exotic, rare metal, notoriously difficult to machine and weld, would be the only chance. This was the birth of Project Oxguard. The biggest hurdle for Kelly Johnson and his small, highly specialized team at the Skunk Works wasn't just the sheer physics of sustained Mach 3 flight. It was the material required to endure it. At Mach 3.2, the leading edges of the wings and the nose cone would glow a dull cherry red, reaching temperatures well over 800 degrees Fahrenheit, 427 degrees Celsius. Aluminum, the workhorse of post-war aviation, would turn to slag. High-strength steel was too heavy. The only viable solution was titanium alloy, specifically the expensive and frustratingly volatile B120VT. Titanium had the necessary strength-to-weight ratio, could withstand the extreme thermal cycling of the Mach 3 environment, and, critically, possessed a low radar cross-section, helping with the plane's burgeoning stealth requirements. But there was a colossal problem. In the early 1960s, virtually the entire global supply of high-grade titanium ore and processing capability was dominated by the Soviet Union. The very adversary the aircraft was being built to spy on. This created one of the most brilliant and audacious logistical maneuvers of the Cold War. Johnson needed to acquire enough titanium in huge sheets and billets to build dozens of the largest aircraft of its kind, and he needed to do it without alerting the Soviets to the U.S.'s sudden, immense appetite for their strategic material. The CIA stepped in, executing a masterful covert purchasing operation. They established a complex network of dummy corporations, front companies, and foreign shell entities across Europe and Asia, creating a convoluted supply chain that meticulously masked the end user. The metal was purchased through these intermediaries, sometimes from Soviet-allied nations, often directly from Soviet suppliers who were none the wiser, believing they were selling the precious metal for innocuous commercial purposes, like manufacturing golf clubs or simple construction. Back in Burbank, the engineers faced the challenge of actually building with the exotic metal. Titanium was notoriously difficult to work with. Machining it required specialized, razor-sharp tungsten carbide tools and a copious flood of cooling fluid, lest the titanium catch fire, becoming a brittle, worthless mess. Welding was an absolute nightmare. Oxygen was the enemy. Even a trace amount could contaminate a weld, making it brittle and weak. Johnson demanded welding be performed inside custom-built, sealed chambers where the atmosphere was replaced by inert argon gas. These clean rooms resembled underwater diving bells more than fabrication bays, and the technicians, often working blind or through thick rubber gloves, had to master an entirely new process of fusion welding. The sheer scale of the titanium required was staggering. The airframe for the resulting aircraft, the A-12, the CIA's original designation for the single-seat reconnaissance version, would be constructed of approximately 93% titanium. Kelly Johnson had not only specified an impossible aircraft, but he had also compelled American metallurgy to perform a crash course in large-scale titanium fabrication. Every jig, every tool, and every procedure had to be invented from scratch under the incredible pressure of a ticking clock, driven by the memory of the U-2 wreckage still smoldering in the Russian dirt. The men working on Oxcart were pushing the boundary of not just aerodynamics, but industrial science itself, all while the raw material for their secret weapon was arriving, often unknowingly, straight from the enemy's hands. With the material problem tentatively solved, Kelly Johnson turned his attention to the core aerodynamic and thermodynamic challenge, managing the intense, destructive heat generated by sustained Mach 3 friction. The temperature on the skin was one thing, but the heat soaking into the interior, into the fuel, the hydraulics, the electronics, and the pilot was an entirely separate monster. At such speeds, the heat was so great that standard JP-4 jet fuel would vaporize instantly, turning the fuel tanks into bombs and starving the powerful engines. Johnson's solution was elegant, counterintuitive, and utterly brilliant. The fuel itself would become the coolant. He demanded the creation of a completely new type of jet fuel, one with an extremely high flash point and thermal stability. The result was JP-7, a synthetic paraffin-based hydrocarbon that could handle temperatures that would melt conventional engine parts. Critically, JP-7 was so thermally stable that it required a shot of a chemical, triethylborane, to ignite it during engine startup, a visible flash of green fire that became a signature of the aircraft. The entire airframe was designed as a massive, integrated heat sink and thermal management system. The JP-7 was routed through a complex web of heat exchangers. It would absorb the crippling heat from the hydraulic fluid, which was reaching temperatures of 600 degrees Fahrenheit, and from the sophisticated reconnaissance electronics, before being fed into the massive Pratt and Whitney J-58 turboramjet engines. The airframe literally used its own highly specialized fuel to prevent itself from cooking to death. This integrated thermal design dictated the aircraft's famous flowing shape, the elongated, chined forebody that ran almost the entire length of the fuselage, serving multiple purposes, reducing radar cross-section, generating lift, and, crucially, maximizing surface area for thermal dissipation. The design was revolutionary, but it demanded a level of sealing integrity that had never before been achieved. The aircraft would expand by several inches due to thermal growth once it reached cruising speed and temperature. This expansion meant that when A-12 sat cold on the ground, its fuel tanks, which were integral to the structure, not separate bladders, leaked. They leaked constantly, puddling JP-7 beneath the sleek titanium wings. Johnson simply deemed it an acceptable compromise, a necessary price for Mach 3 flight. "The leaks stop when you take off and heat up," he famously quipped. The Skunk Works team also had to tackle the issue of the cockpit environment. The pilot was essentially flying inside an oven. Traditional refrigeration would be too heavy and ineffective. Instead, a complex environmental control system was engineered to circulate a frigid nitrogen-rich air mixture through the pilot's customized, fully sealed pressure suit. The pilot was flying in a personal, climate-controlled bubble, completely isolated from the hostile environment just inches away. Kelly Johnson had engineered a system where every component, from the fuel to the air ducts, had to fight a constant, invisible battle against the tyranny of thermodynamics. The demands of Project Oxcart placed an unprecedented burden on engine technology. No conventional jet engine could operate efficiently or reliably across the entire flight envelope of the A-12, from subsonic takeoff speeds up through the sustained Mach 3 cruise. Kelly Johnson needed a power plant that could breathe air like a jet at low speeds, but act like a rocket's propulsion system at high speeds, handling massive airflow and extreme heat without seizing. He turned to Pratt & Whitney to deliver what became the iconic J-58 turboramjet. The J-58 was not just an engine. It was a thermodynamic transformer. Below Mach 2, it operated as a conventional, albeit immensely powerful, turbojet. Air was sucked in, compressed by multiple stages of fan blades, mixed with the unique JP-7 fuel, and ignited. But as the A-12 accelerated towards cruising speed, the air compression needed for the turbojet cycle would become thermally and mechanically impossible. At Mach 3, the air entering the engine would already be approaching 800 degrees Fahrenheit. If it were compressed further by traditional fan blades, the temperature would soar past the melting point of the metal. The J-58's genius lay in its bleed air bypass system, effectively turning the engine into a ramjet, a duct that compresses air by forward speed alone, while the jet was still climbing. As the Mach number increased, sophisticated, hydraulically actuated spike cones located in the engine inlets automatically moved inward. This movement choked the supersonic airflow, creating a series of powerful shock waves that slowed and compressed the air before it reached the fragile compressor blades. By Mach 2.2, nearly 80% of the massive thrust was being generated by the air bypassing the compressor entirely and being mixed with fuel for burning in the afterburner section, effectively making the engine a giant, high-efficiency ramjet with a minimal thrust turbojet strapped to its nose for takeoff and acceleration. The power output was staggering. Each J-58 could generate over 32,500 pounds of thrust in afterburner, a total of 65,000 pounds of force propelling the titanium aircraft. The fuel consumption was equally breathtaking. At full speed, the two engines together would burn over 1,000 gallons of JP-7 per minute, giving the aircraft an operational range that demanded multiple, highly complex mid-air refuelings by specialized KC-135Q tankers. The successful integration of the variable inlet spikes, the bleed air system, and the robust titanium construction of the J-58 made it the highest-performing air-breathing engine ever built. It was a complex, temperamental, and absolutely necessary technological leap. Without the J-58, the Mach 3 dream remained just that, a dream. Kelly Johnson had pushed not only airframe construction, but the very limits of propulsion physics into an entirely new realm of performance. As the airframe and engine problems were being violently solved with titanium and thermodynamic wizardry, Kelly Johnson also grappled with the aircraft's fundamental purpose: surveillance without interception. The U-2 had been shot down because it was visible to Soviet radar and could not outrun their missiles. The new aircraft, the A-12, had to be effectively invisible, or at least have such a drastically reduced radar signature that the Soviets couldn't track it long enough to launch an accurate intercept. This was the birth of operational stealth technology, decades before the public knew the term. Johnson understood that while raw speed was its primary defense, a low radar cross-section, RCS, was essential for survivability. The challenge was immense, as the A-12 was a massive, twin-engine aircraft, a naturally strong radar reflector. The typical rounded shapes of aircraft were anathema to stealth. They tended to scatter radar energy back to the source. Johnson and his team took an uncompromising approach. They eliminated curved surfaces wherever possible, introducing the distinctive, razor-sharp chins that ran along the fuselage from the nose to the wing roots. These chined edges, instead of reflecting radar back, deflected energy sideways and away from the transmitting source. The vertical stabilizers were deliberately angled inward, a design feature that further minimized radar return. Every joint, seam, and access panel had to be designed not just for structural integrity against thermal expansion, but also to minimize radar scattering. The aircraft was coated in a specialized, thick black paint that served two critical functions. First, it dissipated the high heat generated by Mach 3 friction. Second, and most importantly, it was a radar-absorbent material, RAM. This coating was infused with microscopic iron particles designed to absorb and dissipate radar energy as heat rather than reflected. The process of applying this RAM was painstaking and the material itself highly sensitive, requiring meticulous handling in a controlled environment. This black finish, designed to defeat radar and heat, eventually gave the aircraft its famous, intimidating moniker, the Blackbird. Even seemingly minor components became major engineering hurdles. The engine inlets and exhaust nozzles, often strong radar reflectors, were treated with special coatings and structural designs to suppress radar energy. The canopy glass had to be a fused quartz composite containing continuous metallic filaments to reduce the radar reflectivity of the pilot's helmet and the interior electronics. Every external surface was a carefully calculated compromise between aerodynamics, thermodynamics, and electromagnetics. The resulting radar signature, while not zero, was reduced to that of a small conventional fighter, making tracking at extreme range and altitude practically impossible for the existing Soviet systems. The A-12 wasn't just designed to fly fast, it was designed to disappear. The complexity and unprecedented secrecy of Project Oxcart demanded a proving ground unlike any other. Building the aircraft in Burbank was one thing, but testing a Mach 3 titanium spy plane required a vast, isolated stretch of airspace and ground infrastructure, far removed from prying eyes, both domestic and foreign. The location chosen by Kelly Johnson and the CIA was a desolate patch of Nevada desert, known only by its geographic reference, Groom Lake. It would soon gain global notoriety under its unofficial, secretive name, Area 51. Starting in 1960, Groom Lake was rapidly transformed from a dusty, abandoned airbase into a state-of-the-art covert facility. The security was absolute and multi-layered. All personnel involved, engineers, technicians, pilots, and security guards, were subjected to intense background checks and signed lifetime, non-disclosure agreements. Access was governed by a strict need-to-know policy, even within the tight-knit Skunk Works team. To the outside world, the activity at Groom Lake was explained away as high-altitude atmospheric research or generic aircraft testing. The remoteness was crucial for safety as well as secrecy. The first test aircraft, the A-12, was an entirely new class of vehicle operating at the extreme boundaries of human knowledge. Crashes and unforeseen technical failures were statistical inevitabilities, and Johnson needed the freedom to troubleshoot and recover without public or geopolitical scrutiny. The vast, flat salt beds of the lake provided an ideal extended landing strip, crucial for an aircraft with notoriously tricky, high-speed landing characteristics. Getting the finished A-12 components from Burbank to Area 51 was a clandestine logistical nightmare. The massive titanium sections and later, the complete aircraft, were carefully disassembled and loaded onto custom-built, heavily secured truck convoys. These convoys moved exclusively at night, under military escort, utilizing complex routes designed to avoid population centers and curious onlookers. The secrecy surrounding these movements was so tight that the trucks were often accompanied by armed security personnel with orders to prevent any accidental unveiling of the radical new airframe. At the desert base, the team lived and breathed the A-12. The isolation fostered a unique, intensely dedicated culture. There was no room for error, and the pressure to succeed was immense. Kelly Johnson made frequent, intense visits, often flying in himself to personally oversee modifications and address engineering bottlenecks. Area 51 became the crucible where the theoretical physics and groundbreaking metallurgy of the Blackbird coalesced into a functional flight machine, one tiny meticulous step at a time, hidden beneath the vast, silent Nevada sky. It was here, miles from civilization, that the impossible would finally take wing. April 26, 1962. A hidden ramp at Area 51, Groom Lake, Nevada. The air was already shimmering with latent heat, even before the sun crested the mountains. The single prototype, designated Article 121, sat like a creature of myth, its titanium skin a dull, heat-treated black, still visibly weeping the necessary, thermally stable JP-7 fuel onto the pristine concrete below. Standing a respectful distance away, beneath the oppressive Nevada glare, was Kelly Johnson. His hands were shoved into his pockets, his posture betraying a rare, almost crippling anxiety. This was not just a test flight. It was the ultimate vindication or crushing defeat of a decade's worth of engineering defiance. The fate of American reconnaissance and his own legendary reputation rested on the performance of the man climbing into that pressurized coffin. That man was Lou Schock, Lockheed's chief test pilot for the project. A quiet, focused individual whose nerves were made of the same titanium alloy as the machine he was about to pilot. Schock was enclosed in the full-pressure suit, a cumbersome, layered garment that felt more like a space suit than a flight uniform, essential for survival at 85,000 feet. He sealed the clamshell canopy shut. The cockpit was narrow, designed purely for the mission, dominated by the array of highly specialized instrumentation required to monitor the unprecedented thermal and inlet conditions. Schock initiated the sequence for the twin J-58S. The ground crew scrambled back. The startup procedure for the J-58 was as exotic as the plane itself. Because the JP-7 fuel had such a high flash point, it had to be ignited with triethylborane, TB, a pyrophoric liquid that bursts into a brilliant greenish-blue flame upon contact with air. There was a sharp crack, followed by a momentary flash of green fire visible from the exhaust nozzles, and then the colossal, hungry roar of the first engine spooling up. A moment later, the second engine caught, and the prototype shuddered to life, the noise swallowing the desert silence hole. The stench of unburned JP-7 and residual TEB hung heavy in the warm air. As Schock eased the throttles forward, the plane lumbered heavily onto the vast lakebed runway. Its low-speed handling was notoriously poor, a trade-off for its Mach 3 performance. The massive, chined wing body provided excellent lift at speed, but at subsonic velocity, it was a beast, prone to high angles of attack and difficult to control. Schock had to build significant speed before rotating. The takeoff run was immense, consuming thousands of feet of runway. Finally, the titanium bird was airborne, climbing steeply. The entire team watched, breath held tight, as Article 121 became a dark, fast-moving silhouette against the sky. Shock's initial tasks were fundamental. Check the stability augmentation system, the hydraulics, which were running fluids so hot it would blister skin instantly, and, most critically, the engine operation in the lower speed envelope. The A-12 was a fragile, complex system at low altitude, designed to come alive only at speeds that would tear conventional aircraft apart. Shock pushed the aircraft through the initial envelope checks, climbing to medium altitude. He was flying a highly unstable machine, held in check only by Kelly Johnson's uncompromising engineering and the nascent electronic flight controls. Then came the first moment of crisis. As he adjusted the throttles on a gentle turn, an alert light flared in the cockpit. Engine inlet spike malfunction. The sophisticated, variable geometry inlet spike, the centerpiece of the J-58's transformation into a ramjet, had failed to fully respond to a command. If the spike geometry was incorrect when accelerating past Mach 1.5, the shockwave would be ingested violently, causing a catastrophic engine unstart, a violent explosion of air and flame that could rip the engine off the wing. Shock immediately stabilized the aircraft, meticulously running through the emergency checklist. He coaxed the system back online, the immense risk of the experimental system slamming home the reality of what they were attempting. The initial flight stayed strictly subsonic, painstakingly building confidence in the airframe. Finally, the day came to attempt the supersonic realm. Shock pushed the throttles into afterburner and felt the massive acceleration. As he closed on Mach 1, he was keenly aware of the sound barrier's ghost, the sudden drag and buffet that plagued early supersonic designs. But the A-12, designed for sustained speed, punched through the barrier with minimal fuss. However, the real test was yet to come, the thermal climb. On a subsequent flight, Shock was ordered to push past Mach 2. The titanium skin began to heat up dramatically. Inside the cockpit, the instruments confirmed the outside surface temperature rising steadily towards 400 degrees Fahrenheit. The complexity of the thermal management system was now at full operational load. Shock could literally feel the heat penetrating the isolation of his suit, a dull, pervasive warmth that the environmental control system struggled to contain. The unique thermal expansion was taking place. The rivets and seams were settling into their hot, operational alignment. The leaks had stopped, as Kelly Johnson had predicted. But as Shock decelerated for the return, the cooling process began, and the fuselage structure audibly creaked and popped as it shrank back to size, the sound a constant reminder of the physical stress the aircraft was under. The flight logs were a mix of triumph and despair. The A-12 could fly faster than anything on Earth, but the maintenance load was paralyzing. Kelly Johnson, examining the post-flight aircraft with a magnifying glass, pointed out minute cracks in the ram coating, signs of stress on the welding seams, and the persistent problems with the complex inlet control system. "We've created a monster, Shock," he grumbled, "and now we have to teach it manners." The next great challenge was not achieving Mach 3, but making Mach 3 reliable, repeatable, and survivable for the reconnaissance equipment that was its entire reason for being. The road from initial flight to operational capability was paved with thousands of hours of painstaking, high-risk testing, far from the eyes of the world. Even as the CIA's single-seat A-12 prototypes were painstakingly achieving Mach 3 reliability above the Nevada desert, a classified program codenamed Oxcart, political and military currents were pushing for a broader, more public application of the technology. The U.S. Air Force, keenly aware of the U-2's vulnerability and the growing global need for high-speed strategic intelligence, wanted a piece of the Mach 3 pie. They wanted a platform not just for the secretive, single-mission capability of the CIA, but a multi-role, operational aircraft capable of supporting massive global reconnaissance requirements. This necessity gave rise to a new variant and a new designation, the State Route 71. Kelly Johnson, ever the pragmatist, accepted the intrusion of military specifications into his pure, low RCS design. The State Route 71 would be larger, heavier, and crucially, a two-seat aircraft. The SR officially stood for Strategic Reconnaissance, a term designated by President Lyndon B. Johnson during the public announcement of the program in 1964, an announcement that intentionally confused the aircraft's true origin and capability. It was originally intended to be designated the RS-71 Reconnaissance Strike, but a slip of the tongue by the president resulted in the now iconic State Route 71, a nomenclature that quickly became official, much to Kelly Johnson's slight irritation. The need for a second crew member, the Reconnaissance Systems Officer, RSO, was a direct acknowledgement of the complexity of the intelligence-gathering mission. The single-seat A-12 pilot, Lou Schock, was already overwhelmed by the sheer mechanics of managing the Mach 3 flight envelope. The critical, minute-by-minute monitoring of the inlet spikes, the engine temperatures, the thermal soak, and the complex fuel transfer cycles. Adding the burden of operating multiple advanced reconnaissance systems was impossible. The State Route 71 RSO would fly tandem, immediately behind the pilot, enclosed in their own separate, pressurized bubble, surrounded by the cutting edge of 1960s electronics. The RSO's domain was a dense jungle of custom-built equipment. The aircraft's mission was twofold: photographic intelligence and signals intelligence. For the former, the State Route 71 carried the massive Technical Objective Camera (TOC) system, a suite of film and electro-optical cameras housed in the fuselage bays, capable of capturing high-resolution images across a swath of 60,000 square miles per hour. At feet and Mach 3.2, the aircraft could photograph a territory the size of California in under an hour. The RSO managed the cycling of these cameras, ensured the precise navigation data, was correctly tagging the images, and monitored the thermal environment within the camera bays, which had to be kept stable despite the scorching outside temperatures. For signals intelligence, SIGINT, the RSO was responsible for operating the sophisticated electronic countermeasures, ECM, equipment. This was the SR-71's secondary shield. While speed and stealth were the primary defenses, the ECM suite was necessary to jam or confuse hostile Soviet radars and missile guidance systems. The RSO had to constantly analyze the electromagnetic landscape below, detecting, identifying, and deploying appropriate jamming techniques in real time, often using the aircraft's specialized, internally mounted defensive systems to spoof incoming radar locks. The difference between an A-12 pilot and an State Route 71 pilot was mastery of the machine. The RSO's role was mastery of the mission and survival in an electronically hostile environment. Integrating the RSO's systems and second cockpit into the existing titanium airframe was not a simple bolt-on job. The structure had to be lengthened and reinforced to accommodate the heavier payload and the RSO's cockpit, which introduced new complications regarding cabin pressurization and thermal stability. The State Route 71 was roughly 10 feet longer than the A-12, extending the already formidable challenge of low-speed ground handling. Every piece of new equipment, the radar mapping system, the highly accurate inertial navigation system, ANS, the defensive jammers, added heat, weight, and complexity, forcing Kelly Johnson's team to refine and re-engineer the thermal management and cooling systems yet again. The State Route 71 was now more than an airplane. It was a highly integrated, manned satellite flying on the edge of the Earth's atmosphere. It represented the fusion of extreme flight dynamics, advanced stealth concepts, and cutting-edge sensor technology, all packaged into a single, breathtakingly fast vehicle. It was the ultimate defiance of the Soviet surface-to-air missile threat, ensuring that no secret on Earth could remain hidden from American eyes, thanks to the pilot in the front and the complex systems operator in the rear. A typical operational mission for the State Route 71 Blackbird was an exercise in extreme planning, precision logistics, and controlled violence against the laws of physics. It began hours before dawn at one of its forward operating locations, most famously Kadena Air Base in Okinawa, or RAF Mildenhall in the UK. The environment around the aircraft was almost laboratory clean. The sensitive titanium required meticulous handling, and the airframe was constantly monitored for microscopic cracks and thermal damage. The crew, the pilot and the RSO, suited up in their bulky, customized David Clark full-pressure suits, a requirement not just for the high altitude, but as a defense against the crippling heat of a cracked canopy or failed environmental system at Mach 3. Inside the cockpit, the atmosphere was a mix of 100% oxygen and nitrogen, pressurized to an equivalent altitude of about 26,000 feet, even when the aircraft was cruising at 85,000. The Blackbird could not carry enough fuel for a full mission takeoff and cruise. Its engines, the J-58S, were notoriously thirsty. Therefore, the mission began immediately with an aerial refueling. Shortly after lifting off, often in the low-visibility hours before sunrise, the Blackbird, wallowing sluggishly under its massive fuel load and the poor low-speed aerodynamics of its giant body, would rendezvous with its faithful companion, a KC-135 Q tanker. The Q designation indicated a tanker specially modified to carry and dispense the JP-7 fuel. Mid-air refueling was a harrowing dance, even in optimal conditions, performed at high subsonic speeds and medium altitudes. For the state Route 71, the procedure was especially delicate. The sleek, black aircraft had little tolerance for the buffeting and turbulence near the massive tanker. The pilot had to maintain perfect station just behind the tanker's drogue, guiding the long refueling boom into the receptacle on the spine of the Blackbird, often fighting the instability of the heavy aircraft. This first drink was essential, topping off the unique fuel supply before the real ascent began. With the tanks full, the pilot would point the Blackbird towards the edge of the atmosphere and commence the acceleration phase. This transition was the most critical part of the flight. As the aircraft climbed and approached Mach 1.8, the RSO would initiate the complex sequence to convert the J-58S into their high-efficiency ramjet mode. The pilot slowly advanced the throttles, and the massive, sharp inlet spikes began their precise, gradual movement backward into the nacelles, managing the shockwave pattern with millimeter accuracy. This required absolute concentration. If the spikes were even slightly mispositioned, the engine would suffer an unstart, a violent instantaneous loss of thrust on one side, which slammed the aircraft into a hard, uncontrolled yaw that could tear it apart. When an unstart occurred, the RSO and pilot had mere seconds to execute a coordinated recovery, typically involving manually overriding the spike controls and rapidly cross-feeding fuel to prevent a flameout on the remaining engine, all while the fuselage was shuddering under G-forces. It was a constant reminder that they were flying a barely tamed explosion. Once past Mach 2.5 and pushing 70,000 feet, the aircraft was finally in its element. It would then stabilize at its cruising speed of Mach 3.2, approximately 2,200 miles per hour, and its operational altitude of 85,000 feet. The pilot had to maintain the precision of the Mach number to within 0.02 Mach, using the J-58's efficiency sweet spot. Outside, the titanium nose cone reached its operating temperature of over 800 degrees Fahrenheit. Inside, the pilot and RSO were encased in their chilled suits, staring down at the curved, amber-hued windscreen that was now radiating a faint, palpable heat. The Blackbird was now effectively flying faster than any missile could reliably track it, and higher than any manned enemy interceptor could even approach. The pilot's only significant tasks were to monitor the engine performance and keep the aircraft on the razor-thin flight path determined by the sophisticated inertial navigation system, INS. The RSO, however, was now fully engaged, flipping switches and activating the vast array of sensors, ready to capture the vital intelligence from the dizzying, impossible height of the stratosphere, cruising in what felt like the soundless, black void of space. The Blackbird was invincible, for now, but its mission had just truly begun. At Mach 3.2 and 85,000 feet, the Reconnaissance Systems Officer, RSO, in the rear cockpit was the true frontline warrior of the Blackbird's mission. While the pilot maintained the razor-thin margin of error required for Mach 3 flight, the RSO was engaged in a complex, multi-layered electronic battle against the Soviet air defense network below. The mission was not just about taking pictures. It was about operating in an actively hostile electromagnetic environment. The RSO's primary focus was the Type 2 Integrated Reconnaissance System, IRS, an advanced package designed to vacuum up intelligence across a vast spectrum. This suite included the powerful, long-range optical bar camera, OBC, which continuously scanned the terrain below using a rotating prism, exposing film at a phenomenal rate to capture the highest resolution images from the edge of space. The RSO was responsible for monitoring the OBC's performance, ensuring the temperature-sensitive film and optics were functioning correctly, and managing the intricate process of switching between different sensor modes, including infrared and electronic intelligence, ELINT, gathering systems. Crucially, the RSO was the Blackbird's electronic warfare, EW, master. Soviet air defense radars were powerful and ubiquitous, and although the Blackbird stealth features, RAM coating and shine body, reduced its radar signature, it was never invisible. The Soviets could detect the state Route 71. The key was preventing them from achieving a solid, high-fidelity track necessary to guide their long-range surface-to-air missiles, like the improved SA-5 Gammon. The RSO's console was a riot of flashing lights, audio tones, and scrolling text, continuously updating the electronic order of battle below. When Soviet radar illuminated the Blackbird, an immediate, often frantic, electronic dance began. The RSO had to rapidly identify the type of radar system, assess its threat level, and deploy the appropriate defensive countermeasure using the aircraft's onboard electronic countermeasures, ECM, equipment. This involved selecting and tuning powerful jammers designed to flood the enemy radar screens with noise, creating false targets, or breaking the radar lock. The tension during these maneuvers was palpable. A key threat indicator was the constant, low-level missile launch prediction warning provided by the aircraft's advanced threat detection system. Because the Blackbird flew so fast, any detected missile launch was not an immediate crisis, but a complex problem of physics. The RSO had to calculate, in real time, whether the missile, even traveling at speeds exceeding Mach 4, could intercept the Blackbird at its current altitude and velocity. The general rule was that the Blackbird had only to maintain its speed and altitude to outrun the missile's effective envelope, forcing the Soviet weapons to simply run out of fuel or aerodynamic control in the thin air. The RSO's job was to ensure the missile never got a clean enough tracking solution to be accurately fired in the first place. On several documented occasions, Soviet missile sites in places like North Vietnam and the Middle East did launch volleys at the state Route 71. The experience, though terrifying, proved the Blackbird's fundamental defensive doctrine: speed is life. During one mission over North Vietnam, multiple SA-2 missiles were launched. The RSO observed the radar lock breaking as the missile climbed into the thin air, losing energy and coherence. The pilots and RSOs often described seeing the missile contrails, white lines of frustrated vengeance, slowly dissipating far below the aircraft's cruising altitude, a powerful, visual confirmation of Kelly Johnson's genius. But the speed was a double-edged sword. Every defensive maneuver, every course adjustment, every subtle change in power setting could trigger the dreaded engine unstart, a failure that was far more dangerous to the Blackbird than any Soviet missile. The RSO and pilot had to work in absolute, synchronized harmony, one battling the forces of enemy physics, the other battling the forces of aerodynamic physics, both dependent on the fragile, roaring titanium shell that was their protection. The RSO was the man who ensured the intelligence was gathered and that the 30-ton technological marvel, and the pilot, made it home safely. It was a role that demanded encyclopedic technical knowledge, iron nerves, and the ability to make mission-critical decisions in less time than it takes a conventional jet to cross a football field. For the state Route 71 pilot, the Mach 3 cruise was less a thrilling sprint and more a complex, high-altitude tightrope walk. Kelly Johnson had engineered an aircraft that was only truly stable and efficient within an extremely narrow operational envelope, the so-called sweet spot between Mach 3.1 and Mach 3.3 and between 80,000 and 85,000 feet. Deviating from this sweet spot meant immediate loss of fuel efficiency, and worse, risk triggering a catastrophic engine unstart due to improper shockwave management. The pilot's primary focus was the automated flight and inlet control system, AFIX, the nervous system of the J-58 engines. The AFIX constantly managed the position of the movable inlet spikes to maintain the perfect supersonic shockwave pattern inside the engine nacelles. At Mach 3.2, the internal shockwave, which slowed the air down from supersonic to subsonic before it hit the turbine compressor, had to be positioned precisely at the inlet's lip. If the pilot accelerated too much, or if external conditions like a slight yaw, turbulence, or even a tiny control input caused the shockwave to move forward, it would be violently expelled, causing the unstart. An unstart was a terrifying event. It was not just a sudden loss of thrust on one side, but a near-instantaneous, asymmetrical drag that physically wrenched the aircraft into a violent yaw, sometimes exceeding plus or minus 20 degrees in milliseconds. The force was brutal, capable of damaging the airframe, and, more importantly, distracting the pilot to the point of incapacitation. The pilot had to react instantly, manually manipulating the controls and engine power settings, while the RSO simultaneously worked the complex cross-feed and reset procedures, all while battling G-forces that threatened to overwhelm their senses. Recovery from an unstart demanded superhuman coordination and speed, a true test of the symbiotic relationship between the two crew members. The pilot also had to constantly manage the vast, sophisticated fuel management system. The JP-7 fuel was not only propulsion but the primary coolant, and its weight distribution was crucial for maintaining the aircraft's center of gravity, CG. As fuel was consumed or transferred for cooling, the aircraft's CG would shift dramatically. To counteract this, the pilot had to initiate complex, multi-stage fuel transfers between the various structural tanks to keep the CG within a narrow, safe margin. This was a non-stop background task, requiring detailed knowledge of the transfer rates and the thermal state of the fuel. A mistake here could render the aircraft uncontrollably unstable or overheat the electronics. Another perpetual worry was the cabin environment. The pilot and RSO were encased in their suits, protected from the thin, freezing air outside and the 800-degree heat of the airframe. The integrity of the canopy seal and the pressurization system was non-negotiable. A rapid loss of pressure at 85,000 feet meant almost instant decompression to an altitude equivalent of 43,000 feet. The pressure maintained within the suit, but the thermal shock and extreme hypoxia would still be crippling. The pilot's constant monitoring of the environmental control system and the suit's integrity was a matter of life and death, reinforcing the notion that flying the Blackbird was an isolated, deeply personal struggle against the very environment it was designed to conquer. The psychological toll was immense. Flying the Blackbird demanded sustained, perfect performance at the very edge of mechanical possibility. There was no margin for error, no autopilot to rely on for long stretches, and no friendly air traffic control to hold their hand. It was a pure act of man and machine fusion, maintained by sheer skill and Kelly Johnson's faith that human ingenuity could overcome impossible odds. Every mile traveled at Mach 3.2 was a testament to the pilot's focused discipline and the aircraft's engineered defiance. The operational philosophy of the state Route 71 Blackbird was elegantly brutal in its simplicity: outrun the threat. Kelly Johnson had fundamentally shifted the paradigm of reconnaissance from stealth and evasion, the U-2 model, to speed and altitude, the Blackbird model. While the state Route 71 utilized nascent stealth technology, its primary defense was kinetic energy. Its sheer velocity and height made it practically immune to interception throughout its decades of service. The mathematical reality for the Soviet air defense system attempting to track and destroy the state Route 71 was insurmountable. A standard Soviet surface-to-air missile of the era, such as the formidable SA-5 Gammon, typically had a ceiling below 100,000 feet and a maximum speed around Mach 4. However, the energy required to reach the Blackbird's cruising altitude of 85,000 feet and close the gap against an aircraft moving at Mach 3.2 was immense. By the time a missile reached the Blackbird's altitude, it had expended most of its propellant and was merely coasting, rapidly losing speed and maneuverability in the thin upper atmosphere. If a missile was launched at a Blackbird detected 150 miles away, a reasonable detection range, the missile would have to travel that distance plus climb 85,000 feet. The Blackbird, meanwhile, would cover the 150 miles in less than 4 minutes. The constant, high velocity of the state Route 71 meant that the missile's tracking computer had to predict a future interception point so far ahead of the Blackbird's current position that the slightest error in tracking or atmospheric conditions rendered the solution useless. The margin for error for the interceptor was zero. For the Blackbird, its primary defensive countermeasure was simply to maintain Mach 3.2. This guaranteed invulnerability created a strategic shift. The State Route 71 was not a strike aircraft. It was a psychological weapon of intelligence gathering. It flew openly, confidently, and repeatedly over the world's most defended areas. The borders of the Soviet Union, North Korea, North Vietnam, and the Middle East, in plain sight, fully aware that the enemy knew it was there, yet remained powerless to stop it. This constant presence generated vast amounts of intelligence and, crucially, projected an image of technological dominance and information superiority. Furthermore, the Blackbird's speed allowed it to rapidly reposition globally, a major strategic advantage. Operating from its forward bases, it could reach almost any crisis hotspot in the world within a few hours. A reconnaissance flight over the Middle East could be launched from the United Kingdom, refueling twice in midair, complete its mission, and return home, all within a standard workday. This global reach made it an indispensable asset during times of high tension, providing critical, timely overhead imagery that could confirm troop movements, missile placements, and strategic capabilities long before slower, more vulnerable assets could be deployed. The grand strategy was a testament to Kelly Johnson's faith in fundamental engineering. He had correctly assessed that the best defense wasn't clever camouflage or revolutionary weaponry, but an aircraft that simply made the geometry of interception mathematically impossible. Speed was the armor, and altitude was the moat. The State Route 71 pilots and RSOs, witnessing the frustrated plumes of missile launches blooming far beneath them, understood this physics lesson better than anyone. They were flying a machine that didn't defeat its enemies with force, but with the elegant, uncompromising application of velocity and height. In the relentless technological arms race of the Cold War, the ability to see and not be seen, and to laugh at the missiles launched in anger, was the ultimate strategic victory. While the State Route 71 Blackbird achieved operational invincibility in the air, its life on the ground was a constant, grueling struggle against its own complexity and the thermal physics it was designed to withstand. Kelly Johnson's defiance of conventional engineering had produced a revolutionary aircraft, but also produced a maintenance nightmare unparalleled in aviation history. The Blackbird's operational readiness rate, the percentage of time the aircraft was ready to fly a mission, was notoriously low, often hovering in the single digits, making the total fleet requirement high for a relatively small number of operational aircraft. The primary culprit was the titanium airframe and the extreme thermal cycling it endured. Every Mach 3 flight stretched the airframe by several inches, and the subsequent cooling process, which took hours, introduced immense internal stresses. Technicians at the forward operating bases, known as Habu hangars, named after a venomous pit viper in Okinawa, where the Blackbirds were based, spent countless hours inspecting every weld, rivet, and seam for minute cracks induced by the repeated thermal shock. The required precision was astronomical. Repairs often involved grinding out and re-welding sections of the fuselage in the controlled, argon-rich environments necessary to to prevent titanium contamination. The specialized nature of the titanium also meant that tooling, spare parts, and qualified labor were incredibly scarce. Mechanics were trained in highly bespoke skills, and every repair manual read like a doctoral thesis on metallurgy. Simple maintenance tasks that took hours on a conventional aircraft could take days or weeks on the Blackbird, driving the operational cost of the program to astronomical levels. It was often cited that a single hour of flight time required over 100 hours of specialized ground maintenance. Then there was the perennial problem of the JP-7 fuel leaks. The fuel tanks were integral to the airframe structure, not seal bladders. On the ground, the aircraft sat cold, and the titanium structure contracted, causing the seals to weep and pool JP-7 beneath the wings. While Kelly Johnson had accepted this as a necessary thermal compromise, it presented a significant logistics challenge. It meant the aircraft could not be loaded with a full fuel quantity until immediately prior to takeoff, and it required specialized handling procedures to manage the puddles of highly volatile, unique fuel. Every operational base needed to stockpile vast quantities of the synthetic JP-7, which itself was costly and difficult to transport and store. The J-58 engines added another layer of complexity. They were massive, powerful, and utterly temperamental. The delicate balance of the inlet spike control and the internal bypass valves meant that any minor anomaly, from a small crack in a bypass duct to a slight misalignment of the spike, could lead to a disastrous unstart at high Mach numbers. The constant, high-speed flow of air and the extreme temperatures caused rapid erosion and wear on the turbine blades and afterburner sections. Engine replacement and refurbishment were frequent, and the process was difficult, requiring dedicated lift equipment and climate-controlled maintenance bays to protect the delicate internal components. The entire system was interconnected and interdependent. The fuel managed the heat expanded the titanium, the expansion caused leaks, and the speed demanded the perfect J-58. A failure in any one area cascaded across the entire system. The State Route 71 was a brilliant concept that demanded continuous, punishing labor from hundreds of dedicated technicians and engineers for every successful mission it flew. It was the ultimate contradiction, a machine built for effortless speed, requiring unimaginable effort to keep functioning. For those who worked on the Blackbird, its elegance was overshadowed by its relentless demand for absolute, meticulous attention, a silent, expensive tribute to the defiance of physics. Clarence Kelly Johnson's leadership and unique methodology were as critical to the SR-71 success as the titanium and the J-58 engine. The Blackbird was not simply the product of large-scale military contracting. It was the ultimate expression of the Skunk Works philosophy, a set of 14 rules for management and engineering that Johnson had institutionalized within Lockheed's advanced development programs. These rules prioritized small, highly integrated teams, minimal bureaucracy, rapid prototyping, and absolute trust between the engineers and the military client. Johnson abhorred the sprawling, slow-moving committees and layered approvals that characterized conventional defense procurement. His first rule was simple. The Skunk Works manager must be delegated practically complete control of the project. For the State Route 71, this meant Johnson had the power to make immediate, critical engineering decisions, to choose titanium, to design the fuel as a coolant, to accept the on-ground fuel leaks, without getting bogged down in endless bureaucratic review cycles. This agility was indispensable when facing problems of such radical technical complexity. When the initial attempts at the J-58's inlet control failed, Johnson didn't convene a massive study group. He assembled a handful of Pratt & Whitney and Skunk Works engineers, locked them in a room, and demanded a solution in weeks, not months. The culture he fostered was one of intense dedication, extreme secrecy, and engineering brilliance. The team building the Blackbird was small, even by the standards of a major Cold War program. This kept communication lines direct and efficient. Johnson insisted that there must be a minimum number of reports required, but essential work must be recorded in writing. This meant his engineers spent their time solving thermodynamic and aerodynamic impossibilities, not writing verbose status updates for distant, uniform superiors. The pressure was internal and immense, driven by the shared vision of creating a machine that could not be caught. Johnson's genius also lay in his ability to anticipate problems and engineer around them with elegant simplicity, even when the resulting design seemed impossibly complex. When faced with a heat problem, he didn't just ask for better heat shields. He designed the entire aircraft to operate at those extreme temperatures. His insistence on an integrated approach, where aerodynamics, propulsion, thermal management, and stealth were all designed simultaneously, resulted in the SR-71's flowing, chined, and functionally beautiful form. It was a masterclass in holistic engineering. His influence extended beyond the blueprint. Johnson was known for his personal involvement on the floor of the hangar, often spotted in the assembly bays, cigarette dangling from his lip, inspecting welds or quizzing mechanics. He maintained an adversarial but ultimately trusting relationship with the Blackbird's crews, treating the test pilots and RSOs as integral parts of the design team, soliciting their feedback on everything from cockpit ergonomics to unstart recovery procedures. Their survival was his ultimate performance metric. Kelly Johnson retired in 1975, but his imprint on the Blackbird program ensured its longevity. He had provided the U.S. military with a capability that was 30 years ahead of its time. The rules he developed for the Skunk Works became the enduring gold standard for how to rapidly and successfully develop revolutionary technology. The Blackbird was in essence a 30-ton flying monument to the power of a small team of motivated, brilliant minds, freed from bureaucracy and led by an engineering iconoclast who believed that nothing in physics was truly impossible to overcome. Beyond its classified missions, the State Route 71 Blackbird left an indelible mark on aviation history by shattering world records for speed and sustained altitude, records that stand to this day, decades later. These flights, sometimes conducted under the guise of training sorties, served as powerful demonstrations of the aircraft's engineered superiority, solidifying its mythological status in the public eye, even as its true capabilities remained shrouded in secrecy. The most famous of these record runs occurred on July 28, 1976. Two crews, flying two different Blackbirds, were designated to tackle the most coveted categories in aviation: the absolute speed record and the absolute sustained altitude record. The goal was not merely to break the previous records, but to obliterate them, demonstrating the Blackbird's unique ability to sustain performance far beyond the transient capabilities of previous record-holding aircraft. First up was the speed record. Major Adolphus Al George, with Major George T. Morgan Jr. as his RSO, took a Blackbird and established a definitive world record for the fastest flight over a recognized course. They achieved a blistering, sustained speed of 2,193.167 miles per hour, Mach 3.3. Crucially, they didn't just touch this speed. They maintained it for the duration of the official course, flying a precise, high-altitude track that required continuous management of the temperamental engine inlet control systems and a massive thermal load. This record surpassed the previous mark by a colossal margin and firmly established the State Route 71 as the fastest air-breathing aircraft ever created. On the very same day, the altitude record was attempted. Captain Robert F. Helt and his RSO, Lieutenant Colonel Larry A. Elliott, piloted their Blackbird to an unprecedented height. They pushed the twin J-58S to their absolute limit, finding the thinnest air the powerful turboramjets could grip. The official, recognized world record they set for sustained horizontal flight altitude was 85,069 feet. This was a record for sustained flight, meaning the crew held this altitude without a constant climb, demonstrating the stable, operational ceiling of the Blackbird. Above this altitude, the air was simply too thin for the J-58S to efficiently compress and burn the JP-7 fuel, leading to the risk of engine flameout. Looking down from that height, the curvature of the Earth was plainly visible, and the sky above was the indigo black of space. These records were not just for prestige. They were a quiet, confident assertion of America's technological edge during a high-stakes period of the Cold War. They communicated, without ever detailing the true reconnaissance mission, that the U.S. possessed a vehicle that operated in a realm untouchable by any rival military technology. The State Route 71 was literally flying faster and higher than any other nation could follow, confirming Kelly Johnson's vision of speed as the ultimate defense. The final, public demonstration of the Blackbird's capability came much later, as the program was being retired. In 1990, during its last official flight from Palmdale, California, to the Smithsonian National Air and Space Museum in Washington, D.C., the State Route 71 set several new, highly publicized city-to-city records. The most stunning was the coast-to-coast sprint from Los Angeles to Washington, D.C., which it completed in just 64 minutes and 20 seconds, averaging over 2,100 miles per hour. As it landed in D.C., the sonic boom was a final, emphatic farewell, a thunderous reminder of a machine born from a single, impossible idea. These records remain unchallenged because the physics and complexity of surpassing Mach 3.3 for sustained periods are so immense, and a strategic need for a manned reconnaissance aircraft at that extreme performance level was eventually superseded by unmanned systems and satellites. The Blackbird cemented its place as the fastest and highest-flying operational jet ever built, a direct legacy of Kelly Johnson's refusal to accept limits. The State Route 71 Blackbird, the ultimate expression of Kelly Johnson's impossible idea, concluded its operational service not because it was defeated by enemy technology, but because it was eventually outpaced by technological progress on the home front. Specifically, the rise of more cost-effective, unmanned, and truly invisible reconnaissance assets. The age of the satellite and the drone arrived, bringing with it capabilities that matched the Blackbirds in data collection, but without the crippling maintenance costs and the physical risk to two highly trained crew members. The official retirement of the State Route 71 fleet came in 1990, driven largely by budgetary pressure from the U.S. Congress, who balked at the estimated $400 million annual operating costs to keep the small fleet airworthy. Though the pilots and RSOs and their steadfast ground crews argued fiercely for its unique, time-critical global reconnaissance role, the cost-to-benefit ratio, when measured against the capabilities of modern imaging satellites, was deemed unfavorable. The Cold War was effectively over, and the urgent, high-risk intelligence gaps the Blackbird was designed to fill had narrowed considerably. Yet, even in retirement, the Blackbird refused to disappear entirely. A small number of aircraft were reactivated briefly by the U.S. Air Force and NASA in the mid-1990s in response to renewed international crises where rapid, high-resolution, overhead intelligence was needed faster than satellites could be positioned. This short, second life was a testament to the Blackbird's singular capability. The pilots joked that whenever a crisis flared up, the first question asked in the Pentagon was inevitably, "Where's the closest Blackbird?" The enduring legacy of the State Route 71 Blackbird extends far beyond its record books and the millions of miles of classified intelligence film it generated. It is a symbol of engineering defiance. It validated Kelly Johnson's faith that the perceived limits of materials science and aerodynamics were merely temporary barriers waiting to be overcome by disciplined, focused ingenuity. It demonstrated that a small team, given autonomy and clear objectives, could dramatically outperform massive, bureaucratic programs. The Skunk Works philosophy, proven by the Blackbird, became the template for subsequent, crucial development programs, including the first true stealth fighters. Today, the surviving SR-71s sit silently in museums around the world, including the one that set the final record for its flight to the Smithsonian. Stripped of their J-58 engines and their complex sensor packages, they remain potent, aerodynamic masterpieces. Their sleek, black, chined bodies, still exuding a palpable sense of speed even when motionless, serve as a constant reminder of the audacious era in which they were conceived. For the pilots and RSOs, The experience remains a touchstone of their lives. They were members of a fraternity that flew a machine that was often described as an aluminum envelope for a flame, where the air outside the cockpit was so hot it would melt the tools left behind by ground crews, and the very act of flying was a continuous battle against aerodynamic physics. The sound of silence at 85,000 feet, the visible curvature of the Earth, and the thrill of maintaining Mach 3.2 while watching frustrated missile plumes dissipate below. These sensory details define the ultimate experience of Cold War reconnaissance. The State Route 71 Blackbird was more than just an aircraft. It was a technological declaration. It was Kelly Johnson's ultimate response to the threat of the SA-2 missile, a permanent, visible embodiment of American determination to access any information, anywhere, at any time. It achieved the impossible, flying higher and faster than any preceding or subsequent manned jet aircraft, forever cementing its status not just as a machine of war, but as one of the great, pioneering triumphs of aviation engineering. It remains, simply put, the world's fastest ghost.